Okay, 18B number 1. A coin is cost 10 times. The probability histogram for the number of heads is shown at the top of the next page with 3 different shaded areas. 1 corresponds to the chance of getting 3 to 7 heads inclusive. 1 corresponds to the chance of getting 3 to 7 heads exclusive, and 1 corresponds to the chance of getting exactly 6 heads. Which is which and why? Okay, number 1, what does that tell us? Getting 6. The only shading is on the number 6. What about number 2? 3 to 7 exclusive. So if we exclude 3 and 7, but we count everything in between, we're essentially shading all of 4, all of 5, and all of 6. And if we do 3 to 7 inclusive, that would be graph number 3, because we are shading 3 and 4 and 5 and 6 and 7. Does anybody have questions about that? When do we need to worry about endpoints? If you want your answers to be really specific when you shade norm, then you need to use endpoints. Okay? But when should you always use endpoints? No. No. There are kind of 2 ways to describe it. If you don't have a lot of draws, okay? And the reason you want to do that when you don't have a lot of draws is because you have wide columns. So everybody flip back to page 316. On that first graph of 100 tosses, should you do endpoints? Probably. Those columns are kind of wide. They're not as wide as they could have been. But the bottom one, 900 tosses, do you need to do endpoints? Endpoints aren't really going to matter much because the width of each column is tiny. And what we're talking about is this. Let's say that my average is 50, and there's 50, here's 49, here's 48, and here's 47. If I wanted to know how much area is there between 47 and 50, well, our old way of shade norm would only include this much. And we've excluded this piece and that piece, which are relatively large. So if you have a small number of draws, your columns are going to be wider. And if your columns are wider, you need to do endpoints to make sure that you include everything. Now, if we had a similar graph and my columns were super narrow, then the difference between this and this is so small that we don't really care. Where's the breaking point? It all depends, but 100 is pretty standard. But it just depends on how accurate you want to be. Right? If you're developing a drug that might kill people, always use endpoints, no matter what. No matter how many draws you do. But if you are just trying to figure out how tall people are in Emory County, and you only talk to 100 people, you can get by without them. If you talk to 500 people or 1,000 people, then endpoints aren't really going to make much of a difference anyway. So you can always use them, but sometimes it doesn't really help to use them. But if you have a small number of draws, then you definitely want to do endpoints. Okay, number 5. A coin is tossed 10,000 times. Estimate the chance of getting 4,900 to 5,500 heads. So we need to build a box. What goes in my box? A 1 and a 0. Now we could have 6 1s and 6 zeros, but a 1 and a 0 is good enough for us. And eventually, we're going to quit putting tickets in the box. So eventually, we'll just stop putting tickets in there, and we'll use something different. Originally, our box had H's and T's, and we got rid of H's and T's and turned them into numbers. And then later on down the road, we're going to get rid of the tickets altogether. But it's not too difficult. So the sum of the box is 1. The average of the box is 1/2. What is the SD of the box? It's also 1/2. Now, if you don't know that, you can always do big minus small times the square root of the big fraction times the small fraction. But you essentially get the square root of 1/2 squared, which is just 1/2. And anytime you have a single 1 and a single 0 in a box, you will end up with an SD of 1/2. Okay, so my expected value for 10,000 draws is 5,000. Plus or minus, so we have to take 1/2, we take the SD, times the square root of the number of draws, and the square root of 10,000 is 100, so 0.5 times 100 is 50. So, oh, they weren't very nice to us, were they? So we want to know if our average is at 5,000, and 4,900 is over here, and then 50/50 is right there. So basically, we are 2 SDs below and 1 SD above. So I will need to do shade norm. Shade norm from -2 to 1. And I get 81.8. Could you have done that in your head? How would you have done that in your head? Using our fancy 68, 95, 99.7 rule. So the 1 SD rule is 68, and the 2 SD rule is 95, and we essentially have half of a 68 rule on the right side, and then half of a 95 rule on the other side. So 34 plus 42.5, 47.5, that sounds better. And that gives me 82.5, which is pretty close. All right. If I wanted to do from 4,900 to the right, I would shade norm from -2 to infinity, but I'm smarter than that. The middle area is 95, which means there's 2.5 on either end, and I'm just going to add this to that, and I get 97.5. So was the answer 97.5 or close to 97.5? Okay, and then the last one is 50/50 and more. So this area here. Well, my middle area is 68 for 1 SE. So half of that, well, oh, sorry. So that means there is 32 left in both wings. And we only want one of those, which is 16. So the answer is about 16%. And that's how we used to find areas before we had shade norm. Well, really what they did was, instead of having a 1 table, they had like 5 tables. They had a middle area table, they had a right only table and a left only table, Um, I guess 3 would have been enough because you could have done, right? You could have said like from -2 to the right. So, all right, that's how we did it in college. I didn't know. I didn't know the shade norm existed back then. All right, that's it, right?